All right, college chemistry, welcome back. We're kind of looking at our next piece of the KMT puzzle, and that's starting to dig into our gas stoichiometry. Now, if you think about all of the ways that we start to think about pressure, it's kind of been our focus as we think of kinetic molecular theory, as we think about the three factors that can affect our pressure. We can change the temperature, which is going to cause our particles to speed up, collide with more force, increasing the pressure. We can change the volume, which would affect the size of the box. The box is smaller, particles collide more often, they collide with the container more often, pressure increases. And the third way we can change pressure is with the number of moles. Now, we saw in a previous video from Mr. McDonald that we can actually calculate all of these different properties together with that ideal gas law, PV equals nRT. And we found that for any gas, if you have 1 mole of gas under standard temperature and pressure conditions, that's 1 atmosphere of pressure, 273 Kelvin, 1 mole of any gas will always equal 22.4 liters of volume. And that is what we call the molar volume. That is a universal kind of constant when we think about all of our gases. And that becomes really important to us because that means we now have a way to go directly from moles of gas to liters of gas. We have an additional conversion factor that we can use when trying to keep track of or to kind of mathematically determine how many particles of gas are zipping around or are now going to start to react. Because we've used moles before. We've seen moles when we've done our stoichiometry, we've done our mole train, we've seen how we can use that to predict how much of a substance we should get at the end. And that's what we're digging into now. And our new conversion factor is this molar volume, 22.4 liters. Now, because that is true for all gases, that 1 mole equals 22.4 liters, if you under STP conditions, we actually get to shortcut a little bit. This means that if we want to go right from liters of a gas to liters of a different gas, we can actually just use the mole ratio as a liter or volume ratio, because it is going to be proportional. It is the same 22.4 liters for all of our gas particles. Now, it gets a little tricky if one thing's in moles or something's in grams and the other thing's in liters, and we'll look at how you would navigate that. But kind of the new idea or the new piece here is that if you're going from liters of a gas to liters of a different gas, you can use the mole ratio as a volume ratio. So for example, if we take a look on 5.9, if we're looking at number one says if we react 2 liters of nitrogen, what volume of hydrogen would be needed at STP? Well, if we're looking at a ratio, it's 1 to 3. However many nitrogen you have, you need 3 times the amount of hydrogen. Well, if you had 2 liters of nitrogen, you would need 3 times the liters of hydrogen. So that'd be 6 liters of hydrogen. And if we want to know how many ammonia would be produced, or the volume liters of ammonia, well, we would take it times 2. We would take our 2 times 2 to get a new volume of our ammonia of 4 liters. And this has to do, again, with the fact that 1 mole of any gas under standard temperature and pressure conditions is 22.4 liters. Now, if you're not at STP conditions, well, then you might have to use that pivot, PV equals nRT, solve for moles, do your mole ratio, and then plug it back into pivot. Just kind of depends on the situation. Most of these are going to be under STP conditions, but it'll just kind of depend on the information that you've been given. So 22.4 liters equals 1 mole. Only at STP. Important to keep that in mind. So let's talk real briefly about how we can start to navigate these problems. And then I want to look at a couple example problems, make sure you're feeling okay, and how we start to navigate. So wanted to start with a little bit of review. If you remember, we have in the past, we've seen kind of our mole train before. Oh, that's not what I want. There we go. We know that we can go from grams of a substance, grams of, I don't know, I'm going to call it substance A, and we can actually change that into moles. We've done this before. We can change that into moles of substance A. To go from grams of anything to moles of something else, we're going to use the molar mass. You're familiar with this. Again, we've done this before. And we know that based on our balanced chemical equation, we can go from moles of one thing to moles of something else, moles of B, using our mole ratio. Mole ratio. And then if we needed to, if we wanted to get back to like a theoretical yield, we could go back to grams of this new substance. If we wanted to figure out how much we were going to expect, using again now the molar mass, this time for substance B. This is what you've seen before, right? Sorry, way back here at the beginning of the molar mass of substance A, right? But now the question becomes, well, what if you were given a volume? Now, assuming we're at STP conditions, if you're given liters of a substance, doesn't matter what it is, of some substance, and you wanted to get it to moles, you would have to use that molar volume. That 1 mole of any gas will always equal 22.4 liters. This lets us get from moles to liters or liters to moles. If we then were in moles of A, we could change it into moles of substance B, and then we can go back to, if we needed to, liters of our new gas, using, again, 1 mole equals 22.4 liters. So you can kind of think of it like a modified mole train. We're adding on this kind of way to deal with our gaseous particles, depending on what it is we're measuring or what it is we're trying to get to. Now, you'll notice that the conversion factor is the same for the kind of getting from liters to moles and getting from moles back to liters. And as a result, again, this is why you can kind of truncate this idea of our mole ratio. We can make it a liter ratio if we're going from liters to liters. Well, here, let me show you. Hopefully you got that. I need to slide my screen just a little bit so we can look at our next example problem. So if we're looking at number 1, for example, what volume of hydrogen, so we're looking for volume of hydrogen, so we're looking for liters, would be required to produce 0.400 liters of our hydrochloric acid gas at STP conditions. STP conditions is important because that means that 1 mole of any gas is going to equal 22.4 liters. And now we can set it up. This is still just dimensional analysis. We're looking at stoichiometry. Our given value was 0.400 liters of hydrochloric acid. We know that for 22.4 liters of any gas, in this case hydrochloric acid, it will always equal a mole of that gas. That gets our liters to cancel. Now we are into moles of hydrochloric acid. Now we can get from moles of HCl to moles of hydrogen, which was the stuff we were interested in. That's coming right from our ratio, from a balanced equation. That's for every 2 moles of acid gas, that's fun. We need 1 mole of our hydrogen gas to react. Our moles hydrochloric cancel. Now we're in moles of hydrogen. And we know that for 1 mole of any gas, it's going to be 22.4 liters. Oh, and here's the math part, right? Because you got 22.4 in the denominator in the first one and on the numerator in the second one, they cancel out. And again, it's really just this ratio we could potentially use as a volume ratio, assuming we're staying at STP. So it's going to be 0.4 essentially divided by 2 with 3 significant figures. We come out to 0.200 liters. Cool. This would be of our hydrogen gas. Cool. So just taking this idea, because oftentimes our volumes of our gases are pretty large, and so we'll measure those directly. Cool. Let's jump down to number 4 and look at another type of problem here today. 4 says, let's get us some space to work here. Come on, 4, you can do it. There we go. 4 says you've got 50.0 liters of hydrogen gas reacting with 2.3 moles of chlorine gas at STP, which is the limiting reactant. Oh, throwback to limiting reactants. So we're going to have to figure out which one of our reactants makes the least amount of product. And if you remember, when we navigated these types of calculations in our previous unit, we always end up running 2 separate calculations. I'm going to set up my givens, and I've got 2.3 moles of chlorine. So now we can go ahead and solve for the same final product. In this case, I'm going to keep it simple. I'm going to solve them both for moles of HCl. You could go all the way to liters, but that's just going to add an extra step. I'm going to solve them both for moles of HCl because I don't really want to know how much I'm going to have left over. I just want to know which one makes the least amount or runs out first. We're starting in liters for the first one. So we would use our 22.4 liters. Oh, wait, I'm assuming I'm at STP. There it is. Haha, STP, we can use this. Is going to equal 1 mole of this gas. In this case, it is hydrogen. Liters cancel, I'm into moles. And then for my balanced chemical equation, I know it's 1 mole, it's implied, of hydrogen will make 2 moles of hydrochloric. Cool, so for every 1 mole H2 gas, I can make 2 moles of my hydrochloric. Ooh, sorry, get a little scribbly here. Cool, so we're going to have 50 times 2, which I think is 100, divided by 22.4, which comes out with 3 sig figs, 4.46 moles, assuming it has enough chlorine to react. Well, let's look at our chlorine. I'm in moles, so I can start right with my mole ratio. For chlorine, it is a 1 to 2 as well. For every 1 mole of chlorine, I make 2 moles of hydrochloric acid. My moles of chlorine cancel. 2.3 times 2, I think, comes out to 4.6 moles of hydrochloric acid. Well, we'll never make that much. We'll never get to make 4.6 moles worth of hydrochloric acid because we're going to run out when we make 4.46 moles, which means it is our hydrogen. So our hydrogen gas is the limiting reactant. LR is the limiting reactant. Cool. One more example here. Let's take a peek at number 6 today. Let me discard that. Perfect. Get us some room to work. Number 6 is a little different. In Judgment Day Honest, if you were working in a lab, you'd be less worried about how much of your extra is left over, because really you want to know how much product are you going to be able to make. But this is a good question, and we can kind of use our shortcut now to help us navigate this, because we now know that if we're going right from liters to liters of something else, we could just use straight up a liter ratio using the mole ratio. Cool. So I think this is another limiting in excess. We've got 200 liters of nitrogen reacting with 500 liters of hydrogen. Which of your reactants is in excess, and how much of it remains unreacted? Okay, so there's kind of 2 parts here. We needed to figure out how much is, or sorry, which one of them is going to be left over, and then how much. So let's just start by finding our limiting reactants. So this is a lot like number 4. And luckily, both of them are already in liters. Didn't specify a pressure or a temperature here. We're going to have to assume that it's STP, because we don't have enough information to be able to navigate this question otherwise. And I'm going to go ahead and just solve these both for liters of the product, NH3. I'm going to solve them both for liters of my ammonia gas, because if I go from liters to liters, it now becomes a 1-step problem. I can go right to my ratio. So in this case, my nitrogen is for every 1 liter of nitrogen gas, I can make 2 liters of my ammonia, NH3. So I think 200 times 2, well, that's going to be 400, right? Going to equal, 400 point. Watch your decimal place here for sig fig purposes. Cool. We can do the same thing for our hydrogen. Our ratio here for hydrogen to ammonia, it's for every 3 liters of hydrogen, I can make 2 liters of ammonia. This one you might have to punch in, right? So 500 times 2 is 1,000, divided by 3 is going to come out to, I think, 333. 333 liters. Aha. Well, looks like we're not going to be able to make 400 liters, which means for the answer to our first question, nitrogen is in excess. Nitrogen is in excess. Now we want to know how much of it is in excess. Well, I always think of the limiting reactant as the boss. It's in charge. If I need to do any calculations, I'm going to use my limiting reactant amount. Sorry, I'm just going to make myself a little more room here. I know I'm going to stop once I use up all 500 liters of my hydrogen gas. It runs out first. I now need to know, well, how much of my nitrogen am I going to need to do that? So now I'm going to solve for my nitrogen. And I'm going from liters to liters, so I can just solve my liters using my liter ratio, which for hydrogen, we got for every 3 liters of hydrogen, we only need 1 liter of nitrogen. 500 divided by 3 gives us 167 liters of nitrogen. And this is how much nitrogen we're going to use. And this is important because how much did we start with? We started with 200 liters. So if we want to know how much is left over, we would take the amount of liters of nitrogen we started with, subtract by the amount we used to find that we're going to have 33 liters of nitrogen gas left over when this reaction has occurred in excess. Cool. So hopefully got 3 good different example problems to be looking at as you start to navigate these problems. If you've got questions, feel free to reach out, either email myself or Mr. McDonald. We'll get you taken care of as we continue to look at our gas stoichiometry.